Dr. R.P. Aditya, Assistant Professor of Mathematics, V.V. Vanniyaperumal College for Women, Virudhunagar. In this video, the definition of countable sets and its examples will be seen. Also, the preliminaries needed for the understanding of countable sets will be seen. The sets, capital N denote the set of all natural numbers, capital Z denote the set of all integers, capital Q denote the set of all rational numbers, Q plus denote the set of all positive rational numbers, and capital R denote the set of all real numbers. So first we will see the definition of a function. For that we are in need of two non-empty sets. So I am taking capital A and B, two non-empty sets. F defined from capital A to B is a function if for each A in capital A there is a unique element small b in B such that A comma B belongs to F. For example, in the first figure, in the set A there are elements 3, 11, minus 2, 9 and 5, and in the set capital B there are elements 10, minus 8, 2, minus 1 and 4. So for each element in capital A there is an unique element in B. 3 is mapped to 10, 11 is mapped to 2, minus 2 is mapped to minus 1, 9 is mapped to 10 and 5 is mapped to 4. So this is an example of a function. Consider this figure. 3 is mapped to 6 and 7. Also 11 does not have any image. Therefore this figure is not a function. Coming to the definition of 1-1 function. So a function f from A to B is 1-to-1 if for each element A of A there is a distinct element of B. It is also known as injective. Consider if small element A1 belongs to capital A and A2 belongs to capital B, f is defined as f from capital A to B such that f of A1 equal to f of A2. So consider this example. The element 10 is mapped to 1, 20 is mapped to 2, 30 is mapped to 3. Therefore, this is an example of an 1-2 function. But in this figure, 10 and 30 are mapped to 3. They are not mapped to distinct elements. Therefore, this is not an 1-to-1 function. Although it is a function, but it is not 1-to-1. Now we will see the definition of onto function. A function f from capital A to B is called onto if for all b in capital B there is an element small a in capital A such that f of A equal to B. Onto function is also referred as surjective function. See this example. Here x is mapped x, small element x is mapped to small a, small y is mapped to small b, and z and w are mapped to C. So for the element in the codomain, so this set is called domain and this is called codomain. So each element in capital B, A has x, B has y and C has z and w. Therefore this is an example of an onto function. Coming to this example, the element small b does not have any pre-image in this set. So this is not onto function. So a function f from capital A to B is called a bijection if it is 1-1 and onto. That is, bijections are functions which is both 1-1 and onto, which is also called injective and surjective. So in the first figure, this is a function, 1-to-1 function, onto function. Therefore, this is the example of a bijective function. Coming to this example, it is a function. But it is not 1-to-1 because z and x are mapped to 1. But it is onto. Therefore, it is not bijective. Coming to this example, x and z are mapped to 1, y is mapped to 2 and 3 does not have any pre-image. So, it is not an example of, it is an example of not bijective function. So, first one is an bijective function. It is not bijective in the sense of not injective and it is not bijective in the sense of not surjective. So a function f is called bijective if it is both 1-1 and onto. And here we will see when will we say two sets are equal and two sets will be say equivalent. So take this example. If A equal to 1, 3, 8, minus 2, minus 7, and capital B equal to minus 2, minus 7, 3, 1 and 8. The elements in both A and B are the same, but they are in different order, but the elements, all the elements in capital A and B are same. Therefore, we will say capital set A is equal to B. Coming to the second example, capital P contains 1, minus 7, 200, 90 and 55, and capital Q contains 1, 2, 3, 4, 5. P and Q have 5 elements, but they are not equal, but P is said to be equivalent to Q. So we can say that two sets are equivalent to each other if the number of elements in both sets are equal. If capital A and B are two finite sets having the same number of elements, then there exists a bijection F from capital A to B. So using all these preliminaries, we are going to define an equivalent sets and countable sets. So every equal set are said to be equivalent, but equivalent set need not be say as equal sets. So two sets capital A and B are said to be equivalent if there exists a bijection F from capital A to B. So for a two non-empty set to be equivalent, there exists a bijection from capital A to B. So consider these examples. In the first example, capital A is taken as n. N is nothing but the set of all natural numbers. Capital B is taken as 2, 4, 6, that is set of all even natural numbers. So then F from capital A to B defined by F of n equal to 2n is a bijection. So A is equivalent to capital B. Also, set of all natural numbers is equivalent to set of all integers capital Z. So if we define a function F from n to Z by F of n equal to n by 2 if n is even and 1 minus n by 2 if n is odd, then we will say the F is a bijection. Since it is a bijection, we will say that n and Z are equivalent. Coming to the definition of countable infinite. So a set capital A is said to be countably infinite if capital A is equivalent to the set of all natural numbers n. So any non-empty set will be said to be countably infinite if it is equivalent to a set of all natural numbers. So a set is said to be countable if it is either finite or countably infinite. So a set is said to be countable if it is either finite or countably infinite. So consider these examples. So in the previous slides, we have seen capital A and capital B are equivalent. So we can say n, so B is equivalent to the set of all natural numbers. So the set of all even number 2, 4, 6 are equivalent to capital N. Therefore 2, 4, 6 is countable. Also consider this set, it is countable since if we define a function F from 1 by 2, 2 by 3, 3 by 4 to n by F of n equal to n by n plus 1, that function is a bijection. Therefore, we will get this set is equivalent to capital N. Therefore, this set is countable. Also, set of all integer is countable. Q is nothing but the set of all rational numbers is countable. N cross n is also countable. So these are the important results related to countable sets. A subset of a countable set is countable. If A and B are countable sets, then A cross B is also countable. Let A be a countably infinite set, and if F from A to B on 2, then B is countable. Countable union of countable sets is countable. Thank you.